Alright everybody, so here we are with another video on the chain rule. So this will be the third one that I've made on this topic. And I wanted to show you another example of the chain rule, but I want to do an application problem too, where it says to use the derivative found by the chain rule to estimate something. And then I want to go a little deeper into that and remind you of some things I've been bringing up over the course of the semester about what the derivative is and what it tells us and how we should interpret it. Uh, and I want to do that in light of some things that are coming up ahead in some of the future assignments. Well, anyway, let's solve this problem the way that it is. I've modeled this problem off of something I put on one of the assignments. Okay, so you'll see something very much like this on our assignment for the chain rule. But it goes like this. It says a consumer good has an initial value of $5,000. Okay. Its value over time can be approximated by this function v of t. So v value t time. 5,000 over 3t plus 1 to the second power. And that's good as long as t is between 0 and 4 and t is measured in years. Now, this function, like if you could plot a curve for this function, it would show you that value is decreasing over time, and that's something we would expect for most things, okay? Sometimes it might be more complicated than that. The value of something might decrease over time and then maybe become so rare and desired that its value starts increasing. Who knows, okay? There are lots of scenarios, but this is sort of a typical scenario, I guess you could say. Anyway, it says calculate v prime of 3 and use this value to estimate how the value will change over the next year. So two parts to that question. First, to calculate v prime at 3, so that's the derivative evaluated when t is equal to 3, part 1. Part 2, use whatever that number is to estimate how the value will change over the next year, okay, from year 3 over the next year. So first, to calculate that derivative, we had a rule for that, the chain rule, and I just think because I've worked this out already, it might be good to have the chain rule here for reference. It says if y is some function u to a power n, then the derivative y prime will be n times u to the power n minus 1 times du over dx. Okay, so that you can read that as u is some function of x, let's say. It might be a function of t or whatever the variable is. We'll bring that power down to the front, take 1 away, n times u to the n minus 1. Then du over dx is the derivative of u with respect to x. Okay, the derivative of whatever this u is, considering that x may be the variable. That's what du over dx means. Okay, so you might say nu n minus 1 times u prime. All right, so when I find the derivative of this function with that in mind, I'll rewrite it as not 5,000 over 3t plus 1 squared, but 5,000 times 3t plus 1 to the minus 2 power, okay? And when I apply this rule, this chain rule is what this is called, right there, okay? Then I will bring down the 5,000. The 5,000 is a constant. Our rules of derivatives also tell us that constant factors can be carried into the derivative. So for our function v of t 5,000 times, our derivative v prime of t will also be 5,000 times. Now, 5,000 times what? Times whatever the chain rule would give you in this case of 3t plus 1 to the minus 2. We bring that power of minus 2 to the front, then we subtract 1 from it, then we find the derivative of 3t plus 1. The derivative of 3t plus 1 is 3. Okay, so we get like so. Taking 3 times minus 2 times 5,000, we'll get negative 30,000 over 3t plus 1 to the positive 3 power. Okay, so there's our derivative. In the first part of this question was calculate v prime of 3. So it's like, okay, v prime there, v prime of 3. I'll put 3 in to this, and I get negative 30. Okay, so there's my calculation. When it says calculate v prime of 3, calculation v prime of 3 is negative 30. Now, next part says estimate how the value will change over the next year from year 3. Okay. Now, I think to do that, we need to think about, well, what does the derivative mean? Like here I see the number -30, but unless I know what a derivative is and what it tells me and where it comes from, unless I know that kind of stuff, I don't have any way to tell you what the number -30 means or tells me. So sometimes we use the notation, this is called Leibniz notation, this du over dx. That would mean the derivative of u with respect to x. And we might say v prime, but in Leibniz notation we would say dv over dt. Okay, so I think my first thought is, well, that tells me dv over dt is -30. Okay, and then my next thought is what that tells me. See how we write dv over dt as our derivative notation sometimes? Well, what that can be thought of is that this number for our derivative, -30, measures change in value over change in time. Okay, so if it measures that, if change in value over change in time is -30, let's put -30 over 1. So it's like, then we see, oh, well, so if the change in time were 1, then the change in value would be -30. Now the 1 is a little bit arbitrary, but as long as we get -30 as a result, we could do it, all right? So we could say -60 over 2, same thing, really. It says if the change in time was 2, then the change in value would be -60. Do you see how this is the same number? It's the same number, really, I mean. Okay, so anyway, we'll interpret it like this. We'll just use the 1. And so it says if time was to change by a year, then value would change by, reduced by $30. So time goes up by 1 year, value goes down by $30. Okay, so that gives me a way to interpret it. It says from year t is equal to 3. I have to say the from t is equal to 3 because this derivative was evaluated with t being 3 in mind. So from year 3, if 1 year were to pass, the value would decrease by about $30. Okay, so that's how we can give an estimation and an interpretation. Okay, all right. Now, at this point, this problem ends, and everything I say after it will just be to explore the concept of the derivative and try to introduce some things that will come up in the future for our class. If you're not interested in that and you just wanted to know how do you solve the problems like this in the homework, then okay, you don't have to watch the rest, right? So, okay, now I say that as a disclaimer just to tell you that, well, what I'm going to say next gets a little bit into the weeds, but I think if you're really going to become good at math and understand it the way economists use it, that what I'm about to say will be useful, all right? So it's not like I'm telling you something for no reason. But it is a little bit into the weeds, I have to admit. So the entire story is more complicated. And what I'm thinking is, like, this was the way that, like, when I saw this problem on my math lab and I put it in the homework, this is the way that the answer was worded that you select from. If 1 year were to pass, the value would decrease by $30. Well, like, do we need the derivative to tell us that? So that's the first thing I want you to think about. Do we need the derivative to tell us something like that? Why don't we just do this? We got our function that calculates the value at any point in time. So how about this? Why don't we calculate the value at year 3, $50. I put 3 in there, tells me the value is 50, and then put the value at year 4 in there, and it says $29.59. So that would be an average rate of change. That's something we learned about a little bit earlier in the semester. For me to do this would be an average rate of change, okay? And so it seems like I don't really need calculus and the chain rule and the derivative to do this, because if I calculate the value for year 3 and year 4 and I subtract, it seems like it would answer that question. So here it's like I've directly calculated the change in the value, and it looks like it reduces by about $20.41 from year 3 to year 4. Does this contradict the answer? Okay, well, so it certainly seems to. Okay, because I told you that the derivative would tell us that from year 3 to year 4, the value reduced by $30. So which is it? Okay, well, so two things. First is that the question actually said estimate how the value will change over the next year. It didn't say to give an exact calculation. All right, so that's fine. I use the derivative, and there's as far as much of an estimation it could tell me, that's what it tells me. All right. So that's first thing. So it didn't say give an exact calculation, it said to give an estimation. All right, so seems to let us off the hook with that. But still, like, doesn't it seem to contradict even that? It's like, why would we even do that then? Why would we use the derivative? Well, to that I would say, well, you know, that's if I had to give a very loose interpretation of what this answer, I guess it could be that. I mean, obviously, it contradicts the exact numbers a little bit. But let me just say that the reason I'm getting such different numbers, like that the derivative tells me from year 3 to year 4, the change in value is going to be 30 bucks. And the average rate of change, or what I would say is a direct calculation to that question, tells me from year 3 to year 4, the price will reduce by $20. Then I would say, well, the derivative is the instantaneous rate of change. And that means that the derivative will compare as a close approximation to the average rate of change if the average rate of change is based on delta t about 0, okay? So here delta t is 1. That's not very close to 0. So the derivative would compare to the average rate of change if like delta t was like say 0.1 or something like that. So as an experiment, let's try that. So here with t being 3 to 3.1, I computed the average rate of change. So that has delta t to be very small, close to 0. And what I'm saying is if I calculate the average rate of change, delta v over delta t, change in value over change in t time, that it will be fairly close to what I get to the derivative. So here I've done that. T is 3, t is 3.1. Here's v of t in each case. I subtract 47.13 minus 50. It's negative 287 divided by 0.1, which gives us negative $28.7 per year. So that's a lot closer, okay? See, we calculate our derivative to be negative $30 per year. And here when I do delta t of 1, I get like something not even close. I get 20. And here when I do delta t to be 0.1, I get something much closer. I get 28.7. Still not equal to 30, but all we're saying is the smaller and closer to 0 delta t is, then the more in alignment and the more equal the derivative and the average rate of change are. Okay, so I know that's into the weeds a little bit, but those concepts are part of how we do calculus and how economists use math. Sometimes, I'm not saying economists use calculus for everything all the time, but that's the nature of calculus, okay? All right, now, so still, like, why would we use the derivative at all and not just do average rates of change like this? If we really wanted to answer such a question, say, how is the value going to change over time? Then I'd say this, like, why use the instantaneous rate of change? Why use the derivative? The derivative can tell us the nature of the curve at different points. So it gives us a kind of precision on our thinking like I'm about to show you, okay? So we might apply it to something like a revenue curve. So suppose we have a revenue curve, meaning it tracks the revenue over various prices, all right? So you might think that you're in the business of selling something and you price it at whatever, and at that price you get a certain number of people interested in whatever that item is, okay? And they're buyers at that price, and then so you get a certain amount of revenue. All right, so that's how revenue could be a function of price, right? That's probably obvious that it is a function of price. It might be a function of other things too, but let's say that revenue right now is visualized just as a function of price. So notice that like the curve like goes up and down, but like what does it tell us about how revenue is sensitive to price? Okay, so I've labeled 4 points on this revenue curve and told you how the derivative has different kinds of numbers at each point, and then what that might tell us about how revenue is sensitive to price. Okay, so here at this point on the curve, point 8, the derivative would be a large positive number because the curve is fairly steep there. And because the derivative would be change in revenue over price, it tells us that an increase in price from this point leads to a large increase in revenue. Okay, so like here I might say because the derivative is a large positive number, it tells us that revenue is pretty sensitive to price. It's going to go up quite a bit for an increase in price. It's very sensitive. It's a small increase in price. Okay. And then now we can go to point B, where the derivative would be a small positive number because the curve's not as steep there. Okay, the slope is smaller. Well, that would say that an increase in price would lead to a small increase in revenue. Okay, so like from point B, revenue is not quite as sensitive to increases in price. Okay, revenue will increase from increasing price, but not by as much as when you're at point A. All right. And point C, f prime x, the derivative is a small negative number. So when you get to this point in the curve, or any point past the peak, then we're finding that increases in price actually lead to less revenue. All right. But here an increase in price would lead to a small decrease in revenue. And then at point D, because the derivative is a large negative number, it would say an increase in price would lead to a large decrease in revenue. So now, the derivative might then tell us how revenue is sensitive to price across various points in the curve. Now, that's something that at the average rate of change wouldn't do very well. Okay, it tells us that, well, if you increase t from 3 to 4, v will decrease from 50 to 29. Like, it tells us that sort of thing. There might be like a loose comparison between average and instantaneous rates of change, or average rates of change in the derivative, but it's not like they're a one-to-one comparison with each other. It still gives us a way to think about it. But the derivative can tell us that, yeah, I mean, like, revenue does depend on price, and we might be concerned about how if you increase price, would that lead revenue to get bigger or smaller, and by how much, and so on. And that's what it does. It explains like the curve like across all of its domain. All right. And then we might be especially interested as economists in points where, like point B, where I see that, well, now I'm increasing price, but I'm getting less and less increase in revenue. That's called like diminishing marginal returns. And then once you get past that, it flattens out and then starts turning around. Then you increase in price, and you start getting less revenue. Okay, so anyway, that's like, I guess, as far as the big picture occurs, what the derivative can tell us, okay, about a curve, whether it be revenue or value or demand or anything. Okay, tells us how whatever that thing is, that function, how it's sensitive to the other variable, and whether the other variable increasing causes whatever it is, revenue, demand, supply, to increase or decrease, and by how much. So I maybe we'll think about it more in those terms in the future. Okay, now, so that's a little bit into the weeds. That's a lot to think about. But calculus is complicated. That's the way that it is. But it is something to think about, and it's part of the bigger picture. And I did give you both sides. I just showed you how to solve this problem, get your number, and how to choose the answer on MyMathLab. All right, so I did give you that. It's easy. I told you that getting into the weeds was optional, but I at least want you to think about both sides.